This is lesson 21.2. In this lesson, we're going to be rearranging pieces of figures into rectangles and seeing how the formulas for area were developed. So we're starting off looking at a figure that kind of looks like a swan, but the swan is made up of figures that we already know how to find the area of, like triangles and parallelograms and squares. But we can also take those same pieces and rearrange them into a rectangle and find the area of the rectangle. So how did the area of the swan compare to the area of the rectangle? Well, since they use the same exact pieces, the areas would have to be equal. So that's what you're putting on number 1. Areas would be equal. And the reason for that is it's the same exact pieces or parts. All right, so let's look at questions 2 through 4 in your notes. So you can develop other area formulas using that same method, taking the figure, breaking it up into parts, and rearranging them into a figure you already know how to find the area of. So we're going to do that with a few figures today. Now, first of all, we've studied rhombuses, or rhombi is really the correct plural of that, and trapezoids before. But a kite is not really something we've mentioned it, but really haven't studied. So by definition, a kite is a quadrilateral. It has 4 sides, but it has 2 pairs of congruent sides that are adjacent to each other, not the opposite sides, the ones that are next to each other. So you can see here I have a figure that is a kite. These 2 red sides are congruent, and these 2 blue sides are congruent. So instead of the opposite sides like a parallelogram, it's the adjacent sides that are congruent. And many times it looks like a kite that you would fly in the sky, like you can see in that picture. So we are going to look at how to find the area of a kite. One property that kites has is very similar to that of a rhombus. The diagonals are perpendicular like a rhombus. But the longer one bisects the shorter one. They don't bisect each other like a parallelogram. Just the longer one, this one here, bisects the shorter one. So you can see the longer one's not being bisected. You have a shorter part and a longer part. But the diagonals are perpendicular, and the longer one bisects the shorter one. So we're going to be looking at some area formulas. They might be formulas that you're already familiar with, and they might not be. But even if they are ones that you're familiar with, you'll see where they developed from. So let's look at our first figure. So this is a kite, and we're going to be looking at finding the area of a kite. So what they've done is they've broken up the area of a kite into 4 pieces and have rearranged them into a rectangle shape. Same pieces, so the area of this rectangle is the same as the area of this kite. So you have these 2 on your notes as well. So we're going to see how to figure out the area of the kite based on this rectangle. So we already know how to find the area of a rectangle. We know it as base times height or length times width. Both of those are appropriate. So the area of a kite is equal to the area of the rectangle, and to find the area of a rectangle, it is base times height. Now let's see where the base and the height of this rectangle came from in respect to the kite. So you can see these 2 blue pieces together made up this longer diagonal of the kite. And the height of the rectangle is half of the other diagonal. So to write the formula, we typically put the fraction 1/2 in front, and we just simply say that the kite's formula for area is 1/2 the diagonal 1 times the diagonal 2, or in other words, 1/2 of the product of the 2 diagonals. The order you multiply them in doesn't matter, because with multiplication it is commutative. So we can just simply write the formula as area equals 1/2 diagonal 1, so I use a little subscript there, times diagonal 2. 1/2 the product of the 2 diagonals. The next shape we're looking at is a rhombus. A rhombus is just a special parallelogram, so we could have, of course, used the formula base times height. That would work as well. But sometimes you're given the diagonals, so we'll need this other formula to use at times as well. So again, the area of the rhombus equals the area of the rectangle because it's the same pieces. And again, we find the area of a rectangle doing the base times the height. So we're going to see where the base and height of the rectangle came from in our rhombus. So the base is this diagonal of the rhombus, and the height is half of the other diagonal. So again, we move that 1/2 to the front of our formula, and we get the same exact formula we did for the kite. So our formula for the rhombus, the area is 1/2 the product of the two diagonals again. Same exact formula that we had for the kite. So our last figure that we're looking at is a trapezoid. We've already talked about the formula for the area of a trapezoid. In fact, we used it in one of our proofs of the Pythagorean theorem, and that was the one that President Garfield came up with. So here is a trapezoid that the pieces have been rearranged to a rectangle. So again, the area of a trapezoid equals the area of this rectangle because it's the same pieces. And again, that's going to be the base times the height. So we're going to see where the base and height of the rectangle came from in respect to the trapezoid. So the base, we have this little green segment we're going to bring down here, is the green segment plus the blue segment. So that's the two trapezoids added together, the two bases added together. The green segment was base 1, the blue segment was base 2, and together they make the base of the rectangle. The height of our rectangle came from half of the height of the trapezoid. Just like with the previous formulas, we usually put that 1/2 up in front. So this is the formula that you should already be aware of for the area of a trapezoid. It is A equals 1/2 the sum of the two bases, so we use subscripts to show that those are different bases, times the height. 1/2 the sum of the bases times the height. Now, it's important that you understand that formulas are always equations. They have two sides. So a lot of times students will just write this part of the formula, but sometimes you're given the area and you're asked to find one of these other variables, like maybe the height. And so if you don't understand that it's an equation and it has two sides, then you don't know where to put your area that you're given. And it goes over here on this side of the equation. So make sure that you always write A equals when you're writing your formulas. So on number 5 in your notes, we're just simply matching the formula with the figure. So remember, for a kite, we said the area is 1/2 the product of the two diagonals. And that was the same thing for the, I didn't do the 1/2, did I? There we go. There it is. And that's the same thing for the rhombus, 1/2 the product of the diagonals. They have the same exact formula. 1/2 the product, which means to multiply the two diagonals. So make sure that you don't leave the 1/2 off, like I dragged that figure right there, and that you don't think you're taking half of both of the diagonals, like is in this formula. Neither one of those is correct. And we're certainly not doubling the product. So it's 1/2 diagonal 1 times diagonal 2. And then for the trapezoid, remember it's 1/2 the sum of the two bases times the height. So there are the correct answers for number 5. Number 6, first of all, this is just reminding you what I told you earlier, that for a rhombus, you really have two formulas now. The 1/2, the product of the two diagonals that we talked about today, and base times height because it's a parallelogram. So whatever information you're given will dictate which one of those formulas you're going to use. So if you're given the diagonals, of course, use this formula. If you're given the base and height, you would use base times height. So it just depends on what information you were given. So question 6 is really a review question. You're given the coordinates of the 4 points of a quadrilateral and asked to classify it with its most specific name. So remember, to classify a quadrilateral using its coordinates, you're going to use the coordinates to find all 4 lengths using the distance formula and all 4 slopes using change in y over change in x. So you're also, once you classify it, going to find the area of that quadrilateral. So go ahead and pause the video here, calculate your distances and slopes, classify your quadrilateral, and find its area. And then you can restart the video to see how you did. Okay, so here are the distances you should have found. Remember, using the distance formula. So for A to B, you're finding the change in your x squared plus the change in your y squared and taking the square root of that. So you should get the square root of 25, which is 5. For B, C, and D, A, since they are vertical segments, you can simply just count those distances and find they are also 5. And then using the distance formula for C to D, again, you get 5. So since all the sides are congruent, you have 2 possibilities for your quadrilateral. It could be a rhombus or it could be a square. So that's why you also do the slope. Now you can probably tell visually it's not a square, but remember, you always want the information to back that up. So finding your slopes, remember, is rise over run. A, B, and C, D both go uphill, so we know they have a positive slope. And when we look at the rise, you go up 1, 2, 3 units, and the run is 1, 2, 3, 4 units. So both of them have a slope of 3/4. Vertical lines, remember, have no slope because you have a change in y, which is your numerator, but you're not going left or right. So your x in change is 0. And when you divide a number by 0, that, of course, gives you an error. That is why it has no slope or is undefined. So we don't see that opposite reciprocal slope that we would need for right angles. So that means it's not a square, it is just a rhombus. To find the area, you could use one of these vertical lines as your base and then use this horizontal distance as your height, because remember, height and base have to be perpendicular. So a vertical and horizontal line are, of course, are perpendicular, forming that right angle. So the base would be the side of your rhombus, which is 5, and if you count this horizontal length, it's a length of 4. So that would be your height. So base times height for the rhombus, 5 times 4, tells you the area is 20 square units. All right, so we learned relearned some formulas for some other figures that we can find the area of now, and that includes a kite, trapezoid, and rhombus. So rhombus we now have 2 formulas for, base times height, and 1/2 the product of the diagonals. And remember, formulas are equations, so that would be A equals. The wrap-up question says, find the area of a rhombus with side lengths of 3 inches and acute angle that measures 45 degrees. So I have that kind of sketched out for us here. We obviously wouldn't want to find the diagonals because we have no way of doing so. So we would use the formula base times height. Now remember, this side length is all of these sides, right? A rhombus has all 4 congruent sides. And so I'm going to use it as the base and then find the height of my triangle, which has to be perpendicular to it. So remember, sometimes your height is outside of a figure like it is here because of that obtuse angle. So I can find that height because of this 45-degree angle. Because this angle is 45 degrees, then I know also I have a 45-degree angle out here, this side making with the base here. So because those are corresponding angles and they have to be congruent since these opposite sides are parallel. So I can use my 45, 45, 90 rules here to find this height. So it's a leg of the 45, 45, 90. The 3 inches is the hypotenuse. So how do we go from the hypotenuse to the leg? We divide by the square root of 2. So when we take the 3, which is the hypotenuse, that's this side right here, and we divide it by the square root of 2, we're going to be finding this leg and this leg both, and this leg would be my height. So 3 divided by the square root of 2, we of course have to rationalize, so we would multiply by the square root of 2 over the square root of 2. So we would get 3 square roots of 2 over 2. So that's my height, and I'm going to multiply that by my base, which is 3. So remember, we multiplied numbers outside together, so that would give me 9 square roots of 2 over 2, and that would be inches squared. Good luck on your homework.